Well, hello everyone. My name is Huan, Feng, and I'm from the Real-Time Computing Laboratory at the University of Michigan. And this is a joint work with Kassem Fawaz, the previous presenter, and my advisor, Professor Kang Shin. In this talk, we're going to investigate an emerging threat, privacy threat, which we call unregulated aggregation of happy user behaviors. And then we will explain how we characterize this privacy threat using a new model we developed, DLG, the Dynamic Linkability Graph. We will give some real-world evidence of this privacy threat by observing how DLG evolved in the real world on real users. And then finally, we will propose our solution, LinkDroid, which is an extension of the Android mobile ecosystem and provides runtime monitoring and mediation of the linkability between mobile applications. So now let's first put our focus on this emerging new threat. Well, you have a smartphone and install different apps on it. And the apps installed on this smartphone, they capture different views of your individual life, such as your political interests, your travel history, how you manage your financial assets, and your online relationships. All these aspects are independent part of your individual life, and therefore should be isolated. However, in the existing mobile ecosystem, once information is collected by the mobile device, it's no longer under your control. Therefore, the information in different isolated islands can be either shared or leaked in any arbitrary ways. Therefore, an adversary is able to link and aggregate different aspects of your life and construct a complete profile of yours. Actually, they can even link this profile to your Facebook app and reveal your real identity. And then here comes the next question. So, in the existing mobile ecosystem, who is capable of controlling multiple applications and do this kind of aggregation? And the answer is there are many, actually. It can be an advertising agency. As we know, most mobile applications have advertising libraries in them, right? And if several different mobile applications embed the same advertising library, this means these mobile applications are sending information to the same entity. And this advertising agency can do whatever aggregation it wants. And it can also be an IT company. As we know, acquisitions happen frequently in the IT industry. In 2013, Yahoo alone acquired more than 10 mobile applications, with Facebook and Google following close behind. After you acquired multiple applications, you also get control over the information of these applications, and therefore is capable of doing this aggregation. And the adversary, of course, can be surveillance agency. As we know, government agencies are particularly interested in the personal life of its people, and sometimes this passed the red line of individual privacy. As has been reported, these surveillance agencies kept monitoring the packets sent through the mobile network, and therefore is able to control information from different sources and do this aggregation. Therefore, we say, in the existing mobile ecosystem, a curious adversary is able to aggregate information of the same user across multiple applications without his knowledge or consent. And we call this the threat of unregulated aggregation of app usage behaviors. And we believe this threat is realistic, financially motivated, and only becoming more promising in the future. Next, let me explain how we characterize this problem using the Dynamic Linkability Graph. Before that, allow me to explain the challenges, right? The problem is here. Here's the overview. Apps collect information. They send it to the advertising agency or IT companies, which may share information with each other and do the aggregation. It's crystal clear. What is the challenge about this? It's challenging because once your information left your device, once your information is collected by the mobile application, there's no way to recall it. Once it left your device, it's no longer under your control. And what happens up there is something you cannot know. Actually, you do not know whether your information has been aggregated or not. Even if they haven't been aggregated at the moment, you cannot promise they won't be aggregated in the future. So essentially, what happens up there in the cloud is a big black box that nobody has control over. Existing works such as PyBox or MolPrive, they propose new computing paradigms. They suggest to modify mobile applications and reduce the functionality of the mobile applications and shift part of the functionality to a trusted cloud provider or trusted operating system, which I agree is useful. However, the problem, it is not compatible with our existing ecosystem, which may become too big to change in a fundamental way. Here, we take a different approach. Our approach can actually be implemented and enforced purely on the client side. The basic idea is characterize and monitor the linkability across mobile applications. We say two apps are linkable if they can associate behaviors of the same user. And this is the prerequisite for any adversary to conduct any kinds of aggregation, and therefore gives an upper bound of the privacy threat. However, as we know that mobile OS provides isolation between mobile applications, so how can two mobile apps know that they're installed on the same device and belong to the same user? And there are two basic approaches. The first one is accessing the same persistent identifying information. We conducted a measurement study from 2013 to 2015 and found that apps are increasingly interested in accessing persistent identifying information, such as your IMEI number or your MAC address. Take one example. In early 2013, 28% of the mobile applications request your MAC address. However, the same number in early 2015 is 55%. Once these two applications get access to the same identifying information, they can conduct whatever aggregation they want up there in the cloud without even trying to bypass the OS-level isolation. An alternative approach is exploiting the IPC channels. Two apps can share user identifiers either explicitly by using intents or using RPC calls built upon the binary protocol, or do this implicitly by writing the identifier first in the shared public storage and then let another app read it. This sounds bizarre, I know, but as we will show later, we actually found apps in the real world that are doing this right now. So specifically in our case, we consider the linkability introduced by 10 different OS-level identifying information and 3 IPC channels. The OS-level information we consider here can be device-specific, such as your IMEI and Android ID. It can be personal, such as your phone number and account number. It can also be contextual, such as the location information and nearby access points. The IPC channels we consider here, it can be explicit, such as sending intents to each other, and it can be implicit, such as reading and writing the same persistent storage. This covers most of the widely used ways of establishing linkability. However, the concept of linkability also extends to other types of identifiers or even side channels, as long as a clear definition is given. So by monitoring the access to this identifying information and the IPC channels, we can construct a dynamic linkability graph during runtime. And the advantage of using this graph to characterize this privacy threat is, first, all the information needed can be get at the client side. We do not need to collaborate with the cloud side or other parties. And second, it actually gives you a number, gives you a quantification of the privacy threat. So allow me to explain more about this DLG. We say two apps are linkable if there's a path between them. So here, app A and F is linkable because there's a path A from D to F. But app A and H is not linkable because there is no such path. Based on this, we define the linking ratio of an app to be the number of apps it is linkable to divided by all applications. So for app A, there are 6 apps linkable to it, and the number of all installed apps is 8. Therefore, the linking ratio of app A is 6/8 0.775. This linking ratio ranges from 0 and to 1, and the larger the linking ratio is, the more linkable this app is to other apps. And another concept which is important is the distance between two apps. We define the distance to be the number of connecting nodes between two linkable apps. So in this case, for app A and B, their distance is 0 because there's no connecting nodes. This means if an adversary wants to aggregate the information in app A and app B, it doesn't require information from an additional third app. For the case of app A and G, their distance is 2. It means for an adversary, if he wants to aggregate information in app A and G, it at least requests information from 2 other additional apps. Therefore, we say the larger the distance is, the harder it is for an adversary to aggregate information. Based on this, we have the linking efforts definition. It is the average distance between an app and all the apps it's linkable to. For app A, there are 3 apps with distance 0, 2 apps with distance 1, and 1 app with distance 2. Therefore, the linking effort of it is 4/6. And the larger the linking effort is, the harder it is for an adversary to aggregate information. The previous 2 definitions are defined for one single app. If we calculate this number for every app in this graph and average them together, then we have the global linking ratio and the global linking efforts. These 2 are very important metric because it actually not only gives the intuition, but also gives you the quantification of the privacy threat. GLR, intuitively, the global linking ratio, it tells the probability of 2 random apps being linkable. This captures the quantity of the linkability in the DLG. And GLE, it captures the average distance between any 2 linkable apps. This gives the quality of the dynamic linkability graph. Actually, the concept of GLE is also used in social network analysis under a different name known as CPL, the characteristic path length. And it is used in social network to tell whether a network is easily negotiable or not. Next, I want to show some real-world evidence of this privacy threat by observing how this DLG evolved in the real world. We implement DLG as a mobile extension, which means instrumenting the Android operating system. We do have some other choices, such as user-level interception and dynamic OS instrumentation. However, they do have some limitations that restrict their application in our case. For user-level interception, it's less secure because all of the enforcement is in the user side. If the user app really wants to bypass that, it can always find a way to do this. And the dynamic OS instrumentation actually is very convenient. However, it only covers the Java part of the code. Therefore, it's not as comprehensive. So what DLG tries to do is monitor various access to OS-level information and IPC channels. This means we need to cover almost all formal ways to interact, for an app to interact with system components. Therefore, we have to instrument several system services, especially system services that provides identifying information, as well as a content provider, intent firewall, and the file system daemon, since we also monitor indirect access to persistent storage. And by deploying this DLG on 13 users during 47 days, we get a representative view and alarming findings. We find that 2 apps on your device are linkable with a probability of 81%. And it only requires 0.2 additional app for an adversary to aggregate information in any of the 2 apps. Moreover, 86% of the apps a user installed are linkable to Facebook, which means your identity. Therefore, it means most of your behaviors on a mobile device are identifiable. All these linkabilities comes from different sources, not just limited to device identifiers. Actually, only using your location information and the nearby access points, the adversary can associate 40% of the mobile applications to your real identity, namely the Facebook app. More specifically, we found that the linkability contributed by different sources are proportional to the percentage of apps accessing each source, except for the case of IP location and nearby AP, because they are quasi-identifiers and they're less identifiable. So for example, as we know, location can identify a user, If someone knows your work address and knows your home address, it can pretty much identify you. However, most of the applications you use, you do not use them at home or at work. Therefore, it means if one app requests location information, it cannot necessarily identify you. And now let's do some functional analysis. There is certainly a lot of linkability in the ecosystem. So are they really necessary to the app functionality? The answer is probably not. Most applications request access to device identifiers. However, they only need an identifier that is unique to itself. They do not need the actual identifier, which is the same and consistent across different applications. And for personal identifiers, even though many applications only require one specific type of account, such as either your Google account or your Yahoo account, they simply collected all the accounts they can get. The same thing happens for contextual identifiers. Even though a lot of apps even do not require location information, they still collect your location information, fine-grained location information, and the nearby access point. This information can be used to construct a unique mobility pattern of yours, which can later be used to identify you. And we also find that apps use IPCs in a rather questionable way. It's actually interesting because we find that sometimes app will report their installation on the same device, telling others, now we are on the same device, let's start to talk. And there are some other cases we find that app can bind to services exported by other applications and exchange user identifiers and other informations. This leaves the OS control totally useless. In one specific case, we find that one app explicitly writes all of the user identifier it finds into the persistent storage, which was later read by 3 other apps. And most of the behavior we talk about here may not be necessary to apps functionality. However, whether they're legitimate or not is subject to the personal preference of the users and the specific application context. Therefore, we think it's necessary to involve user in this decision-making process. So next, let's come to the proposed solution, LinkDroid, which provides runtime monitoring and mediation of the linkability. Well, LinkDroid is designed with practicality in mind. It doesn't require modification of mobile applications. It introduces no trusted parties, and it can work purely on the client side. What LinkDroid tries to do is adding a new dimension to the privacy control on mobile OS. So what it tries to do is monitor how app behaviors implicitly affect linkability, and then provide user opt-out options. This is fundamentally different from most of the existing work, which focus on whether information leaked from the device. And LinkDroid has 3 additional key features. The first one is install time obfuscation. The second one is a dynamic linkability graph powered runtime monitoring. And the third one is an unlinkable mode. So when a user installs an app on a mobile device, the LinkDroid will perform install time obfuscation, which anonymizes most of the device identifiers and cut off this default linkability. So once a user keeps using these mobile applications, whenever a certain app behavior establishes linkability with other apps, we will provide a runtime prompt, which gives a behavior description of the scenario and a descriptive risk indicator as well as a quantitative risk indicator. Then the users are given the opt-out options. We also provide something called the unlinkable mode because we notice there's an interesting property of DLG, the graph. Once a link is established in the DLG, it can never be removed. It is because once you share information, share an identifier with others, you can never revoke it or recall it. But under certain scenarios, the users still want to perform a task that has no interference with links that have already been introduced. Therefore, we provide something called the unlinkable mode, which allows the user to execute this app in a complete isolated environment, cutting off the linkability with all existing apps and even the existing sessions of the same app. This creates the illusion that the user is using this app, using a new instance of this app, which is installed on a complete new device. And these features are enabled by instrumenting certain system components of Android, such that when app talks to these system components, they do not directly get the result. Instead, they will query a linkability service first. The linkability service will then calculate whether this app behavior affects the overall linkability. If so, it will engage the user in this decision-making process and prompt the UI. More details can be found in our paper. We evaluate LinkDroid on the same set of 13 participants as in our measurement, and this is done by replaying the traces we collected in our measurement, adding the LinkDroid features, then asking users to respond to it. We found that the probability of 2 random apps being linkable dropped from 81% to 21%. And we find that the additional apps required to link 2 apps increased from 0.22 to 0.68. This means under most scenarios, an adversary needs to control at least 1 additional app to link information in 2 apps. And we also find that apps directly linkable to Facebook dropped from 86% to 18%. So to demonstrate the effectiveness of LinkDroid, we plot the DLG of a representative user before and after using LinkDroid. And the red dots here represent the Facebook app. As we can see, LinkDroid substantially reduced the linkability. And finally, some takeaways. First, it's important to stop information from being leaked, as we know, and there's tons of work on that. But what I want to propose here, it is also important to make sure that the information that has been leaked or shared will not be linkable unless it is really necessary. And the second is we really enjoy the notion of linkability actually. It's simple, it's clear, and it gives you this privacy guarantee you can make use of. And this concept has been utilized in many other fields, but still seems to be a missing notion in the mobile ecosystem. We hope more people can start to use this and enjoy using this as a useful tool. And last but not least is we believe that user behaviors in mobile applications should be anonymous by default. It shouldn't be an additional feature or a privilege. It should be a basic right enjoyed by all of the mobile users. So I'm ready to take any questions. Thank you.
Jaehyun Jung, Microsoft Research. Interesting work.
Thank you.
So I guess my concern is about sort of other channels that apps can easily use to profile and link, I guess, profile device and then link between these applications running in the same device. For instance, apps can use, the file system is one thing that can easily use to get fingerprint a device, and also accelerometer, and then I guess the next talk we'll talk about some power analysis too. So I'm just worried that maybe your graph gives kind of false sense of privacy to users.
And first, thank you for the question. It's a very good question, actually. We consider this a lot in our design of this work. And the question is basically there are too many ways to establish linkability between mobile applications, and some of the ways can be very covert and difficult to either to find, identify, yes, or tackle. Mm-hmm. And my answer to that is yes, first, it is true. And second is we notice that there are a lot of covert channels or the side channels that you can use to link to apps. However, as we start our management study, we haven't identified any real world case that is doing this. So that's why we put it off in our prototype. This is the first reason. And the second reason is to establish linkability that is really significant. It should be a mechanism that is used by most apps. For example, if you have 100 apps, and only 2 of them are using some covert channels, then it only introduces a very limited linkability in the entire graph. However, I do agree that this is a very difficult problem to deal with, but the concept of linkability is applicable to other side channels and the other identifiers. But there's some technical challenge.
Okay.
Nice work, Shoulenji from Java Tech. So I'm just wondering, because this this linkability graph is dynamic. There's some new edits maybe added, some existing edits maybe deleted. So in this case, how can you accurately calculate the link ability? And the second question is, after you remove so many links from between among these apps, is there any impact on the functions of these apps? Thanks.
And actually, I didn't really catch the first question, so probably you need to ask it again later.
Yeah, the first question is, because this graph is dynamic, so based on this matrix, how can you accurately calculate the link ratio or the measurement?
Anomic or?
Like 0.81, that kind of linkability or something.
Oh, okay. I'll start to answer the second question first. It's like, and the second question is.
Yeah, I mean, when you remove the linkability.
The functional part.
On the function.
Yeah, actually, there are there are a few different sources that you can introduce linkability, and when we try to deal with them, we do take the functionality into consideration. For example, for most of the device identifiers, we directly anonymize them. This is not our invention because a lot of existing works are doing the same thing, and very limited performance degradation or the effect on functionality is reported. So for most of the device identifiers, they only need to be specific to this device. They don't need to be unique to this device. It didn't need to be the actual value. So anonymizing them introduced little functionality overhead. And the second part is anonymizing the personal identifier, which is your phone number and other process. Why we introduced the runtime prompt. And actually the prompt do have some overhead, but according to our evaluation, it's basically 102 prompt per day because we're taking a similar approach as the one that is adopted in the newer Android M, which is ask as first use. And as we can say, even if we take this relatively conservative model, the linkability that is reduced is still substantial. If the user is willing to put more efforts, like to deal with this prompt more frequently, they can definitely enjoy more on linkability. However, this might be too much overhead from our perspective because privacy or security seems to be a second consideration for most of the users.
Okay, thanks. We may talk the first question.
Okay, let's talk about this later.
Alfred Chen, University of Michigan. So so for me, I think some of the links can be more unique, and some of them can be less unique to associate with each other. So do you consider to add some degree into the link so you can just make it just more just make it better in some sense?
Yeah, so as you can see, the graph we have here is a rather simple graph. Right. It has nodes, it has edges, and it doesn't have degree or weight on any of the node or any of the edge. We do think about that, but then we talk about this idea with some other members, and then we find that people do have very different views on this. For example, for the case of some people think it is very important to stop linking between the other apps and his banking app, because it's like banking app is really crucial for him. So he would like to put more weight on the banking app node or the links with the banking app. However, for some other people, they really simply do not care. But we do notice one acceptance is the Facebook app. Almost all users do not want their behaviors to be linked to their Facebook app. Actually, one of the people taking our survey explicitly said, if any apps requested to be linkable to Facebook without very convincing reason, I will directly say reject, even if I lose some of the functionalities. So for this case is we take Facebook app, which the part we are sure as a new metric is the thing we say the identifiable metric, and leave the other part I think I need to deal with the other part in a case-by-case manner because really different people have different opinions.
Great, thanks.
Yeah, thank you.